question involves a power distribution configuration where 4 trailers, each with 100 amps main panels, are being powered from a 600 volts 3-phase source step down to 208Y/120 volts. The connection of the trailers to the transformer creates an imbalance in the load distribution. Trailer 1 draws power from hot A and hot B. Trailer 2 draws power from hot B and hot C. Trailer 3 draws power from hot A and hot C. Trailer 4 draws power from hot A and hot B. This configuration results in the following load distribution. Hot A draws 300 amps coming from trailers 1, 3, and 4. Hot B draws 200 amps coming from trailers 1 and 2. Hot C draws 200 amps coming from trailers 2 and 3. It is generally not recommended to create such a significant imbalance in the transformer load distribution, especially with a substantial difference between the 3 hots. This imbalance can lead to reduced transformer efficiency, increased heating, and the possibility of overloading the transformer. To address this imbalance and achieve optimal performance, it is crucial to reconfigure the connections to the transformer to balance the load distribution. Here is a recommended approach. Firstly, connect trailer 1 to all 3 hots A, B, and C, drawing 100 amps from each hot. Secondly, connect trailer 2 to hot A and hot B, drawing 100 amps from hot A and 0 amps from hot B. Thirdly, connect trailer 3 to hot B and hot C, drawing 100 amps from hot B and 0 amps from hot C. Fourthly, connect trailer 4 to hot A and hot C, drawing 100 amps from hot A and 0 amps from hot C. This revised configuration will create a balanced load of 100 amps on each hot, ensuring optimal performance and preventing potential issues related to imbalance such as overheating and reduced lifespan of the transformer. Balancing the load on a 3-phase transformer is essential for efficient and reliable operation. An unbalanced load can lead to several problems. Firstly, increased current in one or more phases, which can overheat the transformer windings and reduce its lifespan. Secondly, voltage imbalances can occur, affecting the performance of connected equipment. Thirdly, increased neutral current can overload the neutral conductor and create safety hazards. To understand why load balancing is important, it is necessary to consider the basic principles of 3-phase power. In a balanced 3-phase system, the currents in each of the 3 phases are equal in magnitude and 120 degrees apart in phase. This results in a net current of 0 in the neutral conductor and minimizes stress on the transformer. When the loads are unbalanced, the currents in each phase are no longer equal, leading to a non-zero neutral current and increased stress on the transformer windings. The National Electrical Code, or NEC, provides guidelines for load balancing in section 220.42. This section requires that the load be evenly proportioned among the phases to provide the best balance. The NEC also provides guidelines for calculating the neutral load in section 220.61. which is important for ensuring that the neutral conductor is adequately sized. There are several methods for balancing the load on a 3-phase transformer. One common method is to distribute single-phase loads evenly among the 3 phases. This can be achieved by carefully planning the connection of circuits to the different phases, ensuring that the loads are as equal as possible. Another method is to use 3-phase loads whenever possible. 3-phase loads draw current equally from all 3 phases, which helps to balance the overall load in the transformer. In some cases, it may be necessary to use load balancing equipment, such as automatic transfer switches or phase balancing reactors, to correct imbalances in the load. Automatic transfer switches can automatically switch loads between phases to maintain balance, while phase balancing reactors can compensate for imbalances by injecting reactive power into the system. When designing a power distribution system for multiple trailers, it is important to consider the potential for load imbalances and take steps to minimize them. This may involve carefully planning the connection of circuits to the different phases, using 3-phase loads whenever possible, and using load balancing equipment if necessary. It is also important to regularly monitor the load on the transformer to identify and correct any imbalances that may occur over time. By following these guidelines, it is possible to ensure that the transformer operates efficiently and reliably, and that the connected equipment is protected from the harmful effects of unbalanced loads. In this specific scenario with the 4 trailers, the initial configuration resulted in a load of 300 amps on phase A, 200 amps on phase B, and 200 amps on phase C. This is a significant imbalance that could lead to problems with the transformer. The recommended reconfiguration involves connecting trailer 1 to all 3 phases, drawing 100 amps from each phase. This helps to balance the load by distributing the current more evenly among the phases. Trailers 2, 3, and 4 are then connected to different combinations of phases to further balance the load. By following this reconfiguration, the load on each phase is reduced to 100 amps, resulting in a balanced 3-phase system. This will improve the efficiency and reliability of the transformer and protect the connected equipment from the harmful effects of unbalanced loads. In addition to balancing the load, it is also important to ensure that the transformer is properly sized for the total load. The transformer should be able to handle the maximum expected load without overheating or experiencing voltage drops. The NEC provides guidelines for sizing transformers in section 450.3. This section requires that the transformer be rated for at least 125% of the continuous load, plus 100% of the non-continuous load. It is also important to consider the ambient temperature when sizing a transformer, as higher temperatures can reduce its capacity. Proper grounding is also essential for the safe and reliable operation of a 3-phase power system. The grounding system should provide a low impedance path for fault currents to return to the source, which helps to protect equipment and personnel from electrical shock. The NEC provides guidelines for grounding in sections 250.20 through 250.198. These sections cover topics such as system grounding, equipment grounding, and grounding electrodes. In addition to the NEC, there are other industry standards and best practices that should be followed when designing and installing a 3-phase power system. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide guidance on topics such as power quality harmonics and surge protection. When working with 3-phase power, it is important to be aware of the potential hazards and take appropriate safety precautions. These include wearing personal protective equipment, such as gloves and safety glasses, and following lockout/tagout procedures when working on energized equipment. It is also important to be trained in the proper procedures for working with 3-phase power and to be familiar with the relevant safety standards and regulations. In summary, balancing the load on a 3-phase transformer is essential for efficient and reliable operation. An unbalanced load can lead to several problems, including increased current in one or more phases, voltage imbalances, and increased neutral current. To balance the load, it is important to distribute single-phase loads evenly among the 3 phases, use 3-phase loads whenever possible, and use load balancing equipment if necessary. It is also important to ensure that the transformer is properly sized for the total load and that the grounding system is properly installed. By following these guidelines, it is possible to ensure that the transformer operates safely and reliably, and that the connected equipment is protected from the harmful effects of unbalanced loads. The initial configuration described with trailers connected unevenly to phases A, B, and Z creates a load imbalance. Specifically, hot A had 300 amps, while hots B and C each had 200 amps. This 100 amp difference between phase and the other 2 phases is significant and can lead to several issues within the transformer itself. Firstly, the transformer's efficiency decreases. Transformers operate most efficiently when the load is balanced across all 3 phases. An imbalance causes increased losses within the transformer core and windings, converting more electrical energy into heat rather than useful power. Secondly, the transformer will experience increased heating. The uneven current distribution leads to high current density in the windings connected to the more heavily loaded phase, in this case, phase A. This increased current density results in greater heat generation due to I²R losses, whereas the current and R is the resistance of the windings. Overheating can degrade the insulation within the transformer, shortening its lifespan and potentially leading to failure. Thirdly, there's the risk of overloading. While the transformer might be rated for certain total apparent power, the individual phases can be overloaded if the load is not balanced. The heavily loaded phase in this scenario may exceed its current carrying capacity, leading to overheating and potential damage. Fourthly, voltage regulation suffers. An unbalanced load can cause voltage imbalances at the output of the transformer. The phase with the highest load will experience a greater voltage drop, while the phases with lighter loads will have a higher voltage. This voltage imbalance can negatively impact the performance of connected equipment, especially sensitive electronic devices. Fifthly, increased neutral current can occur. In a balanced three-phase system with a Y-connected neutral point, the neutral current is ideally zero. However, with an unbalanced load, a neutral current will flow, which can overload the neutral conductor and create voltage drops. The recommended solution to balance the load involves a strategic rearrangement of the trailer connections. The key principle is to distribute the load as evenly as possible across the three phases. The proposed reconfiguration aims to achieve this balance. The first trailer is connected to all three phases, A, B, and C, drawing 100 amps from each. This immediately adds a balanced load component to the system. Trailers 2, 3, and 4 are then connected to different pairs of phases in a way that compensates for the initial imbalance. Trailer 2 connects to phases A and B, drawing 100 amps from A and 0 amps from B. Trailer 3 connects to phases B and C, drawing 100 amps from B and 0 amps from C. Trailer 4 connects to phases A and C, drawing 100 amps from R and 0 amps from C. When these connections are combined, the resulting load on each phase is 100 amps, creating a balanced three-phase system. This balanced configuration offers several advantages. Firstly, it maximizes transformer efficiency, reducing energy losses and lowering operating costs. Secondly, it minimizes transformer heating, extending the lifespan of the transformer and reducing the risk of failure. Thirdly, it prevents overloading of individual phases, ensuring that the transformer operates within its rated capacity. Fourthly, it improves voltage regulation, providing a more stable and reliable power supply to connected equipment. Fifthly, it minimizes neutral current, reducing stress on the neutral conductor and improving overall system safety. In addition to balancing the load, there are other important considerations for three-phase power distribution. Firstly, proper grounding is essential for safety and to prevent equipment damage. The grounding system should provide a lower impedance path for fault currents to return to the source, allowing protective devices to quickly clear faults. Secondly, overcurrent protection devices, such as circuit breakers and fuses, should be properly sized and installed to protect the transformer and connected equipment from overloads and short circuits. Thirdly, voltage monitoring should be implemented to ensure that the voltage remains within acceptable limits. Low voltage can cause equipment to malfunction, while high voltage can damage equipment. Fourthly, power quality monitoring can help to identify and address issues such as harmonics and voltage sags, which can negatively impact the performance of sensitive electronic equipment. Fifthly, regular maintenance and inspection of the transformer and associated equipment are essential to ensure reliable operation. This includes checking for signs of overheating, loose connections, and insulation degradation. Furthermore, the NEC provides specific guidelines for transformer installations and overcurrent protection. For transformers over 600 volts, the primary overcurrent protection should be set no higher than 300% of the transformer's rated current if using a circuit breaker, or 300% if using fuses rated 600 volts or less. If using fuses rated over 600 volts, the primary overcurrent protection should be set no higher than 300% of the transformer's rated current. On the secondary side, if the secondary current is 9 amps or more, the overcurrent protection should be set no higher than 125% of the secondary current. If the secondary current is less than 9 amps, the overcurrent protection should not exceed 167%, and if less than 2 amps, it should not exceed 300%. These rules are outlined in NEC Table 450.3. The location of the transformer must also comply with NEC regulations. Transformers should be readily accessible for inspection and maintenance. They must also be installed in well-ventilated areas to prevent overheating. If the transformer is installed indoors, it must be in a dedicated room or enclosure that meets specific fire resistance requirements. Additionally, warning signs must be posted to alert personnel to the presence of high-voltage equipment. The grounding system must also adhere to NEC requirements. The transformer's enclosure and all non-current carrying metal parts of the electrical system must be grounded to provide a path for fault currents. The grounding electrode system must be connected to a grounding electrode, such as a ground rod or a metal water pipe. The size of the grounding conductors must be based on the size of the service entrance conductors, as specified in NEC Table 250.122. Proper labeling of the electrical system is also essential for safety and maintenance. All circuits and equipment must be clearly labeled to identify their purpose and voltage. This includes labeling the transformer, the overcurrent protection devices, and the disconnect switches. Accurate and up-to-date electrical drawings must also be maintained to provide a record of the electrical system layout and connections. Finally, all electrical work must be performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Electrical work can be dangerous, and it is important to take all necessary precautions to prevent accidents and injuries. By following these guidelines, the electrical system will operate safely, reliably, and in compliance with all applicable regulations.